Okay, welcome. This is part 3 of Ray Tracing in One Weekend. As a quick recap, the ray tracer we have so far is basically creating a ray, line pointing through space for each pixel in the image that we're creating. And then for each ray we're calling this function to determine what color that pixel should be. And we have a sphere in our world. Here's the center of the sphere and its radius, and we're checking whether the ray that we're sending out hits that sphere or not. And if it does, we just return red. So we don't have any shading or lighting or anything. We just get a solid red. If not, we have this sort of sky blue background. And then for each pixel, we just write a few numbers to standard out. We're using this PPM format, and our script just takes that output from standard out, redirects it into a file, and we end up with an image like this. Actually, let me make it a little bigger while I'm here. Nice. All right, so now it's going to get a little bit more interesting. We're on chapter 6 if you're following along in the book. And we're going to use the surface normals of the sphere to determine what color to show. So a normal is just a vector that points perpendicular to the surface of whatever our object is. And we can figure out the direction of that just by taking the point where our ray hits the sphere, subtracting the center of the sphere, p minus c, as it shows here. So let's jump into the code here a little bit. We're going into the hit sphere method, which currently is just returning a Boolean. So if this discriminant, this is the little bit of math that would go under the square root in the quadratic formula. If that discriminant is greater than 0, we have a hit, we return true. Otherwise, we return false. So now we're going to make this a little more interesting, and we're actually going to return the t, how far along the ray do you have to go to get to the point where it hits. And so now we say if that discriminant is negative, then we just return -1, meaning no hit. And actually, I don't even need to say return, since this will be the end of our function. If it's positive, then we, instead of just returning true, return what is the actual value of t, where the hit is. In Rest, square root is actually a method on numbers, so we can do it this way, and then divide by 2 times a. And it looks like I have a syntax error of some sort. Oh, I see. It's not a syntax error. It's that I changed the type here. Sorry. Okay. So now in ray color, we're still going to call hit sphere, but we're going to take the return value and store it. And then we'll say if t is greater than 0. And now what we're going to do is return a color based on the normal vector. So first we got to calculate that normal vector. So we'll do r dot at t, that's p, that's the point where the ray hits the sphere. And then we'll subtract the center of the sphere, which is a couple lines up there, 0, 0, -1. So that's our normal vector. And then we have to normalize it, meaning scale it down so that it's a length of 1. And we're using the GLAM vec3 type, so we can just call dot normalize to do that. Then if we just returned n itself, we'd have all the values be somewhere between -1 and 1, but we really want them to be between 0 and 1 because that's how we represent colors, with a value of red between 0 and 1, green between 0 and 1, blue between 0 and 1. So we'll take the x, y, and z and add 1 to each of them. So that gives us something in the range between 0 and 2. And instead of adding one at a time like they do in the book, I'm actually just going to do n plus 0.31. And 0.31, this all caps, is just shorthand for the vector 1, 1, 1. So that gives us, again, a vector where all the components are between 0 and 2. So then we multiply by a half to get into the range between 0 and 1. And if you kind of think it through a little bit, it should look like this. When we're farther in the x direction, the positive x direction, x corresponds to red, so we get a redder color on the right. When we're farther in the positive y direction, y corresponds to green, so we get greener on the top, less green on the bottom, and so on. So let's try it out. And there we go. All right. Now, by the way, you might say this is not a very Rust-like way to do things, to have -1 be this sort of magic number that means no hit. This really probably should return an option of F64, where none means no hit and a sum means there is a hit and here's where it is. But for now, I'm just going to follow what the book does. What they do next, I know there's a lot of math, don't get scared. The key thing is just to say, let's define this number h to be b divided by -2. So instead of b here, we could, let's see, what do? They put in an h. And if h is b divided by -2, then we can just take away this multiplier of -2, and that's our h. Here, instead of a dotted with itself, they use length squared. Or excuse me, instead of r dotted with itself, they do r dot length squared. I think I like that approach. Why is it not letting me do that? Oh, r dot direction, sorry. Dot length squared. Okay. C is the same, except instead of OC dot OC, they're doing OC dot length squared. Same thing. And then our discriminant, well, if h is b over -2, then b is -2h. So you can think of this as -2b, or excuse me, -2h times -2h. Well, we can factor out both of the -2's, and so that's just going to give us 4 times h squared. But now we can actually factor out the 4 out of the whole thing, and so this is 4 times h squared minus ac. But then when we take the square root of that down here, we're just going to get 2 times the square root of this. And so we can just take off the 2 here, and this b becomes -2h, so that becomes positive. Okay, so we have 2 times the discriminant, if we use this new discriminant, and 2 times a, and -b is 2 times h. So then we can just factor out all the 2's, and we get a slightly simpler expression and make the CPU do just a little bit less math for us. All right, so far we've been calling hit sphere, and we just have this one sphere, and its center and its radius are hard-coded right here. And so they want to do a little bit of abstraction so that we could have multiple spheres, or maybe even multiple other objects, although in this tutorial it's just spheres. So they define an abstract class for something that's hittable, meaning a physical object that you could send a ray out and calculate where it hits. So this is rest. Of course, instead of an abstract class, we're going to have a trait. And a trait has a hit method, takes self, and a ray, and a tmin and tmax. I'm actually just going to go ahead and use a range here instead, since rest nicely has a range type built in. In fact, unfortunately, it has a couple of them built in. I think we want this one, std ops range. And then they do this very like C++ kind of thing here where they have a hit record that is passed in by reference. And so if there's a hit, you're going to fill in those details as an out parameter, and then you're going to return true to indicate that you filled them in. I think it will be a lot more natural for Rust to just return that hit record, except we may not have it. There might be no hit, and so we have to return an option of hit record. Now, what's a hit record? Right here. It's just a point. Where did the ray hit? A normal vector, what was the normal vector of the surface at that point where it hit? And t is how far along the ray were we when we hit. And now we can define a sphere as something that just has a center and a radius, and it has a hit method. So let's go down below our hit trait and say struct sphere. I'm not going to bother with a constructor. I think when we need one, it only has 2 fields. We'll just construct it directly. This is for making sure you don't pass in a negative radius. I'm going to be a little lazy and just skip that. All right, and now we can implement our hit method, and it's basically this logic, except that instead of just returning the F64, we're going to return the hit record, if there is one. But it looks like all this is the same, at least to get us started. Discriminant is h squared minus ac. And here, center, of course, we mean the center of the sphere we're currently dealing with. So self.center and self.radius. Okay. If the discriminant is less than 0, we return false in the C++ code, which is going to map to returning none in this version. Actually, there's enough code here. I'll just do it this way. Return none, and then we can go here. Just take the square root of the discriminant, and then we got to find the nearest root. So this is, again, solving a quadratic. That means there is, in general, potentially 2 solutions, and we want the one with the smaller value of t. They say root here. I'm actually going to call it t because I think it will make things a little easier in a minute. So h minus that square root over a. And then if t is, here we're saying less than the minimum or greater than the maximum, meaning if it's not in the range, then we'll try the other root, which is going to be h plus that square root. Right, there's that plus or minus in the quadratic formula. Okay. So same thing, if that one's not in the range either, then there's no hit. Okay. But if we make it down to this line, that means it is in the range. One of them, at least, was in the range. We're reassigning t, so it's going to be mute, I guess. And so now we can construct our hit record and return it. So we get some hit record. P is going to be r dot at t. T is just going to be t. And the normal is P minus the center of the sphere divided by the radius of the sphere, so that it is normalized. And so then, of course, we just need to extract P here. Oops. Should be self.radius. Okay, and it's complaining here, expected reference to F64, found F64. Okay, fair enough. Okay, so now we can actually get rid of the hit sphere method, and instead we're just going to have a sphere and call hit on it. But before we do that, they want to know if we're hitting the front or the back of a face. So with the sphere, I guess you could hit the inside if you situated your sphere such that the camera is inside of it. Then the ray would be hitting the inside of the sphere. And you would know that because the outward facing normal and the ray would be pointed more or less in the same direction. And so you might remember that if the dot product between two vectors is positive, it means they're pointing essentially in the same direction or close to the same direction. If it's 0, it means they're 90 degrees to each other, and if it's negative, it means they're pointing generally away from each other. And that's what this is all about right here. So we're determining the outward normal. We're taking a dot product between that and our ray, and we're using that to set, I believe, a Boolean, if I remember correctly. Yeah, this front face Boolean. So that we know if we're hitting the front or the back of whatever surface we're talking about. So we'll add this. And I don't really like this style where we have set most of the fields of the record here, and then we have to call set face normal, because it means that for a moment we have a record that's kind of half initialized. So instead what I want to do is make a new method that we can call, so that by the time you get to the end of the new method, you have a fully constructed, fully consistent hit record. And I think Rust encourages this style, which is nice. Okay. So let's see. So this is going to be hit record new, and it's going to have to take the P and the normal vector and the T, and then it's going to calculate this front face property based on the direction of the ray. So it's going to need to have the ray itself as well, and the direction of the outward normal. Well, how do we know what the outward normal is? It's this same thing that we're calculating here. So I don't think we have to pass that in, or I'm sorry, we're already passing it in right here. So I think this makes sense for our new function. It's going to take a point, a normal vector, t, and then a ray. All right, and then P is just P, the normal is just the normal, T is just T, And then front face is r dot direction dotted with the outward normal. And if that's less than 0, that means we are going at the surface in opposite direction to the normal, meaning it is the front face. If it's greater than 0, we're hitting the back face of it. All right. And then we have to actually calculate the normal here, which is p minus self.center divided by the radius. Okay. Okay, so we have a compiler error here because we're still calling the old hit sphere method that doesn't exist anymore, but we'll come back to that in a minute. But now they want to define a new class that's called hittable list, which is basically just a vec of hittables, or in this case they make it a vec of shared pointer of hittables, but just keep things simple. I'm just going to make it a vec of hittables, or a vec of, since hittable is a trait, I should say a vec of something where that something implements the hittable trait. And rather than create a whole new class here, I am just going to say we can use a vec of h, where h is any type that implements hittable, and that vec will also implement hittable. That's another cool thing with Rust, right, is that you can implement a type from the standard library can implement a trait from your code. I'm going to skip over all this C++ shared pointer. I think is more or less the same as just like RC and Rust. And I'm going to skip over these constants and utility functions because I believe Rust has most of them built in. Infinity, I think you just say f64 : infinity. Yeah. Pi is built in as well. Degrees to radians, I think, is called f64 from or 2 degrees, yeah. Converts radians 2 degrees, or 2 radians, whichever one you need. So we can skip over a lot of that stuff and just go to here, and our ray color function now is going to take a world. So world is just anything that's hittable. So world ref h, where h is any hittable type. And then we're going to say let rec. So we're creating this rec type, and then we're using the return value here to determine if that rec was filled in or not. So instead I'm going to say if let sumRec equals world.hit, we'll pass our ray, and we need a range from 0 to infinity. Well, if that's true, then we are going to have rec be our hit record, and we can use that to determine the color we want, which is basically just that we're going to take the normal vector like we did before. Now it's rec.normal, add 1 to it. Again, we can say vec3 1 and multiply by a half. Oh, this needs to be 0.0. Great. Okay, and then back in the main function, now that we're not hard coding that one sphere, we need to instead say what our world looks like. So it's just a vec of a couple of spheres. First one has a center of 0, 0, and -1, and a radius of 0.5. And the second one, so what they're doing here is they're approximating a flat plane by taking a very large sphere and setting it up so that the surface of it is near the bottom of our image. You'll see what that looks like in a second. Radius is 100. So the center is a little more than 100 units down from the center of our image, but then it has a radius of 100, which means the surface will be right up there. All right, and this is a vec of spheres, which means it is hittable, or it's going to be when I implement that in just a second. And so now we can just pass that in ref world to our ray color function. Okay, so impl hittable for sphere. We also need impl hittable for vec sphere. And I kind of skipped over this part accidentally, so let's go back. Here we go. So we're keeping track of a temporary record, but ultimately that is what we're returning or using as this out parameter. If we do have a hit, we're going to use that. So what I'm going to do is say let temp rec equal none, and then at the end return it. And we don't need this hit anything parameter. We're keeping track of whether we hit anything by keeping track of whether temp rec is none or some. But we do need this closest so far variable, because that is going to change with each hit, so that we make sure that if the ray intersects with multiple objects, we're going to only get the closest one, because it should be appearing in front of all the others in the image. But now we can just iterate through our vector and call object.hit on each item one by one. And we're just going to pass the same ray. For the range, we're going to get a range from the same starting point, range.start, up to this closest so far that we're keeping track of as we go. Hit anything equals true. Well, we represent that by just recording our hit into this temp rec variable. And then we just got to update our closest so far to be rec.t. And the compiler is unhappy. Cannot mutate. Oh, well, I forgot to set that mutable. But it's also going to be unhappy for one other reason, use of moved value. So when we call this line, now we can't use this variable anymore because we've moved it into this variable. So the solution turns out to be quite simple, although it took me a minute, took me a second the first time I went through this. Just set that first, and then set this temp rec. And we're already returning it, so if we got a hit anywhere from any of the spheres, then temp rec will be set to that hit, and if not, it'll just stay as none. All right, so I think this should work pretty good. And does it look like the one in the book? Yes, I would say it does. The next thing they do in the book is use an interval, but I already did that since it's built into the language. I had just already done it. But before I go on to chapter 7, there's one other thing I want to do, and this took me a little while to figure out, but I think I have the right way to do it. This is doing a vec of sphere, but we really want it to be more general. So the first thing is we really want it to be a vec of H, where H is any type that implements hittable, right? So that doesn't really change anything in practice because we only have one hittable type, which is sphere. I guess now, since a vec of sphere is hittable, that means a vec of spheres is also hittable. But so far, that's not very interesting. It doesn't really change anything. But we really don't want to limit it to vec. It really should be any kind of iterable type. So if I made this just an array, for example, like that, well, now it doesn't compile because it says hittable is not satisfied for this array of length 2. It is satisfied for vec, but not for array. So I kind of went back and forth on this a little bit, but I think the right way to do this is to say that hittable is implemented for I, where I is any type that implements into iterator of H. Let's see, trait, where, yeah, I think right. So any type that you can turn it into an iterator and the item that's iterated is H. Any type I that satisfies that should be hittable. But when you turn a vec into an iterator, you lose, you can only sort of do that once. It consumes the vec. So what you really want to do in this case is take a reference to the vec and turn that into an iterator, and then that reference becomes the self. So I think the right way to do this is actually to change the trait definition to take self, not ref self, because if the hittable we're dealing with is a sphere, we don't need to consume it. But if it's an iterator, we do need, not to consume it, but at least to modify it, right? As you iterate through the iterator, you're modifying its internal state. So let's go back up, change this to self, change this to self. Well, now this isn't right because this says that the hit method is going to take ownership of the sphere, and we don't want it to do that. So instead of hittable for sphere, I'll say hittable for ref sphere. And then this into iterator, we do take ownership of the I, whatever that is, but the I could just be a reference to a vec, for example, or a reference to an array, and we can turn that reference into an iterator without consuming the original array or the original vec. All right, and the compiler is complaining to me here. Sphere is not an iterator. The trait hittable is implemented for ref sphere, required for sphere. Okay. Does it make a difference? No, that doesn't make sense. So object is an H. Well, let's see. If I change this, then it's going to be unhappy here because it says cannot move out of world. Oh, okay, so world should be a hittable, not a reference to a hittable. Because then we're going to call hit on the world, and if world is a ref sphere, that's fine, or if it's a list of spheres, that's fine. Um, and then if I just remove this, no, that doesn't work. If I change it to a vec, no, same problem. Okay, so this is an iterator of spheres, but sphere does not implement hittable, only ref sphere implements hittable. Oh. Okay. Great. So all that was a slight diversion, but now I should be able to pass either a vec or an array or a slice or anything that when I take a reference to it, I can then turn that reference into an iterator. And then for each ray, we're going to call this iterate through that iterator and determine whether we got a hit and build our image. All right, I think I will stop there for now and start in the next one with chapter 7.